So if you want a masterclass in building like truly indestructible data pipelines, you really shouldn't be looking at Silicon Valley.
No, definitely not. You need to look uh, about 238,000 miles straight up.
Right, because right now the biggest hurdle to colonizing the moon isn't rocket fuel, it's actually Wi-Fi.
It sounds kind of strange to put it that way, but it is entirely accurate. I mean, we have the physics of spaceflight mostly figured out. The real frontier now is information logistics.
And that is exactly what we are exploring in our deep dive today. We are pulling from this really fascinating article. It was published on datapro.news by Samuel Williams.
Yeah, lunar colonization is a data problem. Great piece.
It really is. And our mission for this conversation is simple for those of you listening. We're going to unpack how the absolute extreme constraints of space travel, the vacuum, the radiation, the massive communication delays, are basically forcing engineers to create the ultimate blueprints for robust AI and data platforms.
Which is so crucial to understand. Because, space exploration isn't just about planting a flag and taking some photos anymore.
Right, the Apollo days are over.
Exactly. The Artemis era is about establishing a permanent, repeating supply chain. It just happens to be a supply chain that runs through a deadly vacuum and endures lunar nights that last for 2 weeks.
Right, so it is essentially the most hostile distributed data platform imaginable. And the best part is that you can actually apply these exact blueprints to your work right back here on Earth.
You really can. But to understand how we were building it, we kind of have to start by completely discarding our favorite Hollywood image of space travel.
Oh, you mean that classic shot of Mission Control in Houston?
Yeah. That giant room packed with people in short-sleeve button-downs nervously watching telemetry on their monitors, that entire model is totally dead.
Wow, really? Just completely dead.
It has to be. I mean, in the Apollo days, continuous human oversight was the foundational assumption of the entire program. You generally had a predictable communication window.
Right.
But when you look at the Artemis architecture, we are putting hardware and people into much more complex orbits, and eventually right on the lunar far side.
And obviously, when a spacecraft dips behind the moon, you have a solid mass of rock between it and Earth.
Exactly. And that creates physical communication blackouts that can last up to 50 minutes.
Let's just pause there because 50 minutes in space, that is an absolute eternity.
Oh, it really is.
If you are dropping out of orbit toward the surface at thousands of miles an hour, you cannot just put the spacecraft on hold while you wait for Houston to reconnect.
No, the physics of the situation completely strip away the luxury of human oversight. It's a fundamental design constraint dictated by orbital mechanics, not, software preference.
So it forces a massive shift from continuous ground control to almost total onboard autonomy.
Precisely.
So it's kind of like it's the difference between micromanaging a remote worker and having to actually trust them to run the whole branch entirely independently.
That's a great way to put it. The old model was pure micromanagement. I mean, every valve turn was vetted by 50 people in a control room.
Right. And now the spacecraft has to make its own life or death decisions when the Wi-Fi drops. But how does that actually change the data we send?
Well,
Because the source mentions a shift from raw telemetry to mission data products. What does that mean mechanically?
think about what raw telemetry actually is. It is just a fire hose of raw state, right?
Mm-hmm.
A voltage level here, a temperature reading there.
There's endless streams of numbers.
Exactly. Just sit back to Earth for a human brain to interpret. But if there are no humans to interpret it for 50 minutes, raw telemetry is totally useless to the spacecraft itself.
Oh, I see.
So the unit of value has to change. Instead of just emitting numbers, the onboard systems have to synthesize those numbers into curated, context-aware mission data products.
Got it.
So the system doesn't just record a temperature spike. It identifies a thermal anomaly, queries the system state, and packages that into a discrete, queryable insight.
Okay, and the source even mentions that they've experimented with an onboard AI assistant to handle this. They describe it as a fifth crew member.
Yeah, an element that can query technical manuals and troubleshoot during these comms blackouts.
Wait, I have to stop you there. Because we've all seen large language models completely hallucinate.
Oh, absolutely.
I mean, they give confidently wrong answers about historical facts or, basic math. Isn't putting an LLM in charge of troubleshooting a life support system in a vacuum incredibly reckless?
That sounds terrifying. Right?
Yeah. What if the fifth crew member hallucinates a procedure for fixing a broken oxygen scrubber and just, vents the cabin?
That is a very valid fear. And it's exactly why the shift to those curated data products is so critical. You absolutely do not feed a generic, unconstrained language model with raw, noisy sensor data in a safety-critical environment.
Okay, so how do they restrict it?
The underlying data pipelines feeding that onboard intelligence are locked down, version-controlled, and exhaustively validated. The LLM isn't like browsing the internet or guessing.
Right, it doesn't have a web search function.
Exactly.
Yeah.
It is essentially trapped inside a highly restricted, perfectly mapped internal knowledge base.
Oh, so it's less of a creative thinker and more of like a lightning-fast librarian that can only read from pre-approved, digitally signed engineering manuals.
That's exactly it. It synthesizes operational manuals
Mm.
and correlates them with those pre-packaged mission data products to prioritize anomalies.
That makes sense.
So the human crew doesn't have to flip through thousands of pages of paper checklists while an alarm is blaring. The system surfaces the exact validated procedure instantly.
Okay, so we have this highly autonomous system operating in the dark. But eventually, the orbital mechanics shift, the moon moves, the 50 minutes end, and the Earth comes back into view.
Right, the connection is live again.
But if the connection is that fragile, how do you actually guarantee that the massive backlog of data you accumulated during the blackout actually makes it across the void intact?
Well, that is where we see the transition from treating connectivity as a nice-to-have to treating it as fundamental infrastructure. NASA is actually building something called LunaNet.
LunaNet, okay.
Yeah, it is essentially a permanent internet backbone for the moon. It provides communications, positioning, and timing services to everything operating out there.
But the core technology running LunaNet is something called delay-tolerant networking, right? Or DTM.
Yes.
And that relies on something called the bundle protocol. Here's my extremely earthbound question, though. Why invent a brand new bundle protocol?
Right, why bother?
Yeah, the entire planet Earth runs on TCP/IP. Why not just beam standard internet protocols to the moon?
It comes down to the assumptions built into how the internet works.
Mm.
Earth's internet protocols fundamentally assume low latency and continuous connections.
Okay.
Like when you load a website, your computer and the server do a rapid-fire handshake.
Yeah.
You there? Yes. Did you get packet A? Yes. Send packet B.
Because the server is usually just a few hundred miles away through fiber optic cables.
Right, exactly. It requires split-second back and forth. But in space, the speed of light is the ultimate bottleneck. A signal traveling from the Earth to the moon and back takes about 2.5 seconds.
That feels fast, but for computers...
For computers, it's an eternity. If you try to do a TCP/IP handshake, the protocol will simply time out before the response arrives.
Oh, so the system assumes the receiving server is dead and just drops the connection?
Precisely. Add in those 50-minute orbital blackouts, and standard internet collapses entirely. So delay-tolerant networking completely abandons the live handshake.
So what does it do instead?
It creates an interplanetary queue using a store and forward mechanism.
Wait, hold on. Store and forward sounds like it receives the data, holds it, and waits to pass it on.
Correct.
But what happens if a relay satellite is holding my critical mission data in its queue, and the satellite experiences a temporary power failure? Does the data just vanish? Like, does the spacecraft crash because the message is gone forever?
That is the exact nightmare scenario DTN is designed to prevent. Because there is no live connection to resend the data, the durability requirements are extreme.
So how does it survive a power failure?
When a node on this network receives a bundle of data, it doesn't just hold it in volatile RAM, it writes it to secure, persistent storage. Literally its own hard drive.
Oh, wow.
Yeah, it might wait 3 seconds, or it might wait 3 days until the next relay satellite comes into view.
Mm-hmm.
Only when it successfully passes the bundle and receives confirmation does it delete the local copy.
So it's less like a live phone call and more like an extremely paranoid, heavily armored postal service.
That is a brilliant way to put it. And the source notes that NASA's Interplanetary Overlay Network is the reference implementation making this real. But the hidden challenge here is schema evolution.
Schema evolution.
Yeah, think about the lifespan of space hardware. You have probes and satellites that operate for 10, sometimes 20 years.
Oh, wow. I didn't even think about that. On Earth, if an engineering team changes an API and accidentally breaks an app, they just push a hot fix an hour later.
You can't do that when your hardware is a decade old and millions of miles away.
Mm-hmm.
If your data schema evolves on Earth and breaks compatibility with a satellite launched 5 years ago, you might lose $1 billion asset.
That's terrifying.
The protocol discipline has to be absolute.
But the payoff for getting this interplanetary queue right is massive. I mean, they are already demonstrating hundreds of megabits per second, aiming for gigabits.
Yeah, it's a huge leap.
We are moving from a tiny trickle of data to an absolute fire hose. And with that much data flowing, you can finally feed the beast of modern machine learning.
Yes, you can.
But as we get into the ML pipelines, the stakes are just wild. We aren't talking about optimizing ad clicks here. We are talking about AI physically operating spacecraft.
Exactly. Lunar colonization demands that systems operate flawlessly when humans are entirely absent. The program relies on orbital space stations like the Gateway and habitation modules like Halo.
Right.
There will be long stretches, months at a time, where these stations are uncrewed. Yet they still have to regulate their internal temperature, manage radiation shielding, and automatically dock with uncrewed cargo deliveries.
And the landing sequences are where the ML really shines, right? The article details a system called SPLAE, which handles descent and landing.
Yeah, SPLACE is fascinating.
It brings together LIDAR, which is basically using lasers to measure distance, and something called terrain relative navigation. If I'm understanding this right, it's essentially acting like a self-driving car, but instead of avoiding pedestrians in real time, it's using machine learning to rapidly classify craters and boulders as it drops out of the sky at blistering speeds.
That is precisely how it works. It takes raw imagery from the cameras, feeds it into onboard terrain models, and spits out actionable trajectory adjustments.
Incredible.
But notice the crucial detail in the source. These are not generic computer vision models. They operate inside a strict safety case.
Meaning what exactly?
The parameters of what the model is allowed to decide are mathematically bounded. It can't just invent a new flight path that defies physics.
Right. And for the ongoing operations of those empty habitats, they have systems like ISEC, which is basically an autonomous caretaker. It really makes you think about the concept of continuous delivery in software engineering.
It really does.
Because on Earth, a bad code rollback means a website goes down. On the Moon, a bad ML update means a spacecraft fires its thrusters at the wrong angle and creates a permanent crater. Autonomy in space is basically a machine learning pipeline with landing gear attached.
That's a great visual. And because failure is so catastrophically expensive, and a software rollback might literally be impossible due to physics, rigorous metadata and provenance aren't just corporate bureaucracy.
They're essential.
They're survival traits. You have to know the exact lineage of the training data that built the model currently flying your multi-billion-dollar ship.
Which brings us to a massive concept in the article, digital twins. They call it simulation-first mission planning.
Right, because colonization is an economic problem as much as an engineering one. The only way to make it affordable is to eliminate surprise entirely.
Because surprises in space are expensive.
Exactly. You use model-based systems engineering to explore every trade-off digitally before you ever bend a piece of metal or burn a drop of rocket fuel.
And the source gives a wild example of this. The Mission Analysis and Integration Tool, or MAIT. They use it to model in situ resource utilization.
Yeah, ISRU.
Basically taking lunar dirt regolith and polar ice and trying to chemically process it into breathable oxygen and drinking water. But how do you actually simulate that? The physical properties of lunar dirt in 1/6 gravity inside a hard vacuum have to be incredibly difficult to predict.
Oh, they are. And this is why a digital twin isn't just a fancy 3D animation to show off in a marketing presentation. It is a rigorous mathematical mass balance equation.
So it's deeply technical.
Highly technical. It has to model the thermal dynamics of baking the dirt, the exact electrical power draw of the machinery, and the fluid flow rates in exact kilograms per hour.
So if a sensor on the actual lunar ice miner detects that the soil is clumping differently than expected, what happens? Does it send that data through our delay-tolerant network?
Yes, exactly. It sends it back, updates the digital twin back on Earth, and then the Earth team simulates a new thermal profile before pushing an updated version-controlled ML model back to the Moon to adjust the baking temperature.
Wow. So it is a constant closed-loop reconciliation between the simulation and reality.
It has to be.
But to make sure that the physical miner, the digital twin, and the ML pipeline actually understand each other, especially when they might be built by totally different companies or even different countries, you need a foundation that is shockingly mundane.
I'm glad you brought that up because it really is the unsung hero here.
Yeah, reading the source material, I was genuinely surprised. We are talking about the pinnacle of human achievement colonizing another world, and it turns out a massive strategic priority is cataloging systems.
Yeah, it sounds a bit dry.
It honestly sounds like library science. Why on earth is a common metadata repository so important?
Well, because the Artemis program is multinational and multi-vendor by design. You have NASA, the European Space Agency, the Japanese Space Agency, plus dozens of private contractors.
Right.
And they're all trying to physically dock their hardware together in orbit and share data pipelines. If one contractor labels a thermal sensor's data output in Fahrenheit and another reads it expecting Celsius, the entire system can literally explode.
Oh, man. So protocols and metadata models are quite literally as structural as the titanium hulls.
They absolutely are.
The source gets incredibly specific here, too. It mentions international standards like CCSDS for file delivery. It talks about data archiving approaches like PDS-4.
Right, which forces engineers to structure science data strictly into source, raw, and derived level.
Yeah, and then there is this deeply technical term, spice kernels, used for navigation and geometry artifacts. What exactly is a spice kernel?
So think of a spice kernel as the foundational grammar rules in a universal translation app, but for geometry. It handles the terrifyingly complex geometry of space. It answers questions like, where exactly is the sun relative to this specific camera lens on the rover at this exact millisecond?
Ah, so if a European mapping instrument is trying to analyze a crater using imagery from an American rover's camera, they need the spice kernel to align their mathematics.
Exactly. Without it, they are just shouting gibberish at each other.
That is fascinating.
And this highlights a profound reality of lunar colonization. Reproducibility on the moon is an operational requirement, not just a scientific ideal.
Because these missions are so long-term.
Right. We're designing pipelines intended to run for decades. An engineer troubleshooting a life support system in the year 2045 needs to perfectly understand a column of data that was structured and named by an engineer who retired in 2026.
Wow. So it's about surviving the generational handover. The naming conventions literally have to outlive the original team.
They do. A metadata repository that can flawlessly index billions of records is the connective tissue that allows anyone in the ecosystem to find a data set, understand its exact context, and trust it enough to bet human lives on it.
Which perfectly brings us to why this matters to you, the listener. Because unless you are secretly building a rocket in your garage,
Which would be impressive.
very impressive, but you are probably wondering how to apply this to your daily work.
Right. And the source directly addresses this, focusing on data engineers working in earthbound industries like finance, retail, healthcare, and energy.
Because space isn't magic.
Yeah.
It is just the harshest possible distributed environment. It holds a mirror up to our field and harshly exposes every single place we tend to cut corners here on Earth.
Exactly.
Yeah.
When you look at how NASA handles data, you realize that building for intermittency, massive latency, and partial failure isn't just for astronauts.
I mean, imagine a hospital network absorbing databases from 3 different rural clinics. If those patient records don't align perfectly, if there is a single dropped decimal because the metadata wasn't governed, that isn't a glitch. That is a lethal medication error.
Exactly. Or think about a legacy bank trying to migrate a 30-year-old mainframe.
Yeah.
If they don't have generational metadata, the system breaks.
It forces you to treat observability as a core product, not an afterthought you just bolt on later.
Yes,
Yeah.
because on Earth, if a server rack goes down, the system usually just panics and crashes.
Mm-hmm.
But on the moon, a partial system failure is just a typical Tuesday.
Right.
Your systems must be designed to degrade gracefully. When you cannot physically walk over to a server room to see what is wrong, your system's ability to explain its own internal state via telemetry is your only lifeline.
It is such an empowering takeaway. We have this futuristic AI, LLMs running habitats, landing spacecraft autonomously married to the most unglamorous ordinary rigor.
Version schemas.
Dependable file transfers, meticulous library science. If you design your Earth pipeline, whether it's a retail supply chain or a healthcare platform, with lunar-level rigor, anticipating latency and planning for the equivalent of a 50-minute blackout, your business platform will be virtually indestructible.
Because true scale does not come from engineering heroics. It does not come from a brilliant developer staying up for 3 days straight to manually patch a database.
No one wants to do that.
Exactly. Scale comes from treating operations as a high-volume, highly governed data environment. The proof that we can survive on the moon is the exact same proof we need to build lasting, responsible AI platforms on Earth.
It really is. To recap our journey today, we started with the death of the traditional mission control, seeing how orbital blackouts force a shift from raw telemetry to curated mission data products.
Right.
We explored how the interplanetary queue swaps out live handshakes for extreme durability, storing data on hard drives to survive power failures.
Yeah.
We unpacked how digital twins use mass balance equations to simulate survival.
And finally, we saw how the meticulous cataloging of metadata ensures those systems can be safely handed down to the next generation of engineers.
It requires an intense amount of discipline, but the reward is operational resilience that can literally survive the vacuum of space.
It really puts a drop Zoom call into perspective, doesn't it?
It absolutely does. Thank you so much for joining us on this deep dive. And just remember, the next time you are stressing out over a server outage or a failed code deployment, take a breath and be thankful your data pipeline doesn't require landing gear.
It certainly makes the day-to-day bugs feel a little more manageable.
It really does. But before we sign off, I want to leave you with one final provocative thought based on our source material. We talk about how the moon will rely on that fifth crew member, the LLM parsing technical manuals and autonomous systems running the habitats when humans aren't around. And we know bandwidth constraints mean we are often only sending curated data products back to Earth, not the raw telemetry. So imagine this scenario. The human crew finally returns to the habitat after a long absence. The astronaut looks at the life support system and fundamentally disagrees with the AI's curated assessment.
Oh, wow.
The human says the system is failing, but the AI confidently reports it's perfectly fine. But because of the bandwidth limits, they lack the raw historical telemetry to mathematically prove the fifth crew member wrong. In that moment of crisis, who do you trust? The astronaut in the room or the lunar-grade algorithm? Something to mull over as you build your own indestructible pipelines.